What specific problem does the new method or algorithm aim to solve?
The new method or algorithm aims to solve the problem of understanding the robustness and sensitivity of large language models, LLMs, to layer-wise interventions, specifically focusing on the deletion and swapping of entire layers during inference. The study investigates the roles of different depths in the network and identifies 4 universal stages of inference in transformer language models: detokenization, feature engineering, prediction ensembling, and residual sharpening. By performing interventions on different layers of GPT-2 and Pythia models, the research uncovers insights into how these models process tokens and make predictions, shedding light on the complex nature of token processing in advanced language models. The study provides a framework for understanding the mechanisms underlying the reasoning capabilities of LLMs and aims to contribute to the field of mechanistic interpretability in neural networks.
How does the proposed method or algorithm work? Illustrate step by step.
The proposed method or algorithm works by investigating the sensitivity of large language models, LLMs, to the deletion and swapping of entire layers during inference. The method begins by performing interventions that delete individual layers or swap adjacent layers in the model. This process helps in understanding the roles of different depths in the network and identifying 4 universal stages of inference: detokenization, feature engineering, prediction ensembling, and residual sharpening. Firstly, in the detokenization stage, the model integrates local context to convert raw token representations into coherent entities. This is followed by the feature engineering stage, where the model builds feature representations based on token context, leading to significant increases in probing accuracy. The prediction ensembling stage comes next, where the model emphasizes relevant predictions while suppressing others, potentially marked by high MLP computation and the emergence of prediction neurons. Finally, in the residual sharpening stage, tokens transition from semantic representations to specific next token predictions. The method involves conducting experiments on different layers of language models, measuring metrics such as KL divergence, relative accuracy, and change in entropy to assess the impact of interventions. The results show that intervening on the first and last layers can have catastrophic effects on model performance, while middle layers are remarkably robust to deletion and minor order changes. By comparing the effects of layer swapping and ablation, insights into the importance and function of each component at different depths in the model are gained. Overall, the proposed method systematically explores the robustness and behavior of language models through layer-wise interventions, leading to the identification of distinct stages of inference and shedding light on the complex nature of token processing in advanced language models.
What are the theoretical or practical benefits of using this method?
The theoretical benefits of using the method described in the paper include gaining a deeper understanding of the stages of inference in transformer language models, which can lead to improved model interpretability and performance. By investigating the sensitivity of language models to layer interventions, the study uncovers 4 universal stages of inference: detokenization, feature engineering, prediction ensembling, and residual sharpening. Understanding these stages can provide insights into how language models process tokens and make predictions, potentially leading to more efficient model training and optimization strategies. Additionally, the method allows for the identification of specialized components within the models, such as prediction and suppression neurons, which play crucial roles in the prediction ensembling stage. Practically, this method can help researchers and practitioners in fine-tuning language models for specific tasks by targeting and optimizing different stages of the inference process. Ultimately, the method contributes to advancing the field of natural language processing by shedding light on the inner workings of large language models and enhancing their robustness and performance.
How is the method validated or tested?
The method is validated or tested by applying drop and swap interventions to every layer of 4 GPT-2 models and 4 Pythia models. The KL divergence between the prediction of the intervened model and the nominal model, the fraction of predictions that remain the same between the intervened model and the baseline model, relative accuracy, and the change in entropy of the prediction between the intervened and baseline model are measured for all interventions. The results show that intervening on the first layer is catastrophic for model performance, causing very high entropy predictions. Swapping the last layer with the second-to-last layer in Pythia models also has a similar catastrophic effect. However, GPT-2 models largely preserve their predictions when subjected to interventions. The middle layers are found to be remarkably robust to both deletion and minor order changes. Comparing the effects of layer swapping and ablation provides insights into the importance and function of each component at different depths in the model. The study also compares the effects of swapping adjacent layers versus ablating layers, showing that swapping is less harmful than ablating layers, indicating that certain operations within the forward pass are commutative.
What results were achieved with this new method?
The new method achieved results that demonstrated the robustness of language models to layer-wise interventions. Specifically, the study applied drop and swap interventions to every layer of GPT-2 and Pythia models, revealing that intervening on the first layer had catastrophic effects on model performance, causing high entropy predictions. Swapping adjacent layers was found to be less harmful than ablating layers, indicating that certain operations within the forward pass are commutative. The study also identified 4 universal stages of inference in transformer language models: detokenization, feature engineering, prediction ensembling, and residual sharpening. These stages were supported by evidence such as the sensitivity of the first layer to ablations, the emergence of prediction neurons around the midpoint of the model, and the presence of suppression neurons in the final layers. Additionally, the study conducted case studies to further understand mechanisms within the models, such as attention heads responsible for constructing multi-token words and the ensembling of prediction and suppression neurons. Overall, the new method provided insights into the complex nature of token processing in advanced language models and shed light on the mechanisms underlying their reasoning capabilities.
What are the limitations or drawbacks of the method?
The limitations of the method outlined in the paper include the inability to definitively pinpoint the specific reasons for differences between GPT and Pythia models, such as whether redundancy originates from dropout during training, structural variances in attention and MLP mechanisms, a higher number of layers, or a combination of these factors. Additionally, the study relies on aggregating data over many tokens, which could potentially mask effects that are specific to certain token classes. Despite these uncertainties, the findings suggest the existence of inference phases across these confounding variables. Further research is needed to address these limitations and explore other references mentioned throughout the text. Future work could involve investigating the stages of inference using sparse autoencoders, SAEs, to provide more evidence, either supporting or refuting the proposed hypothesis.
What future work do the authors suggest?
The authors suggest that future work should address the specific causes of differences between GPT and Pythia models, such as whether redundancy stems from dropout during training, structural variations in attention and MLP mechanisms, a greater number of layers, or a combination thereof. Additionally, they propose further investigations into the stages of inference using sparse autoencoders, SAEs, to provide more evidence for or against the hypothesis of stages of inference. The authors also mention the need to explore the mystery surrounding the final layer of the GPT model, particularly focusing on the anomalous attention spike in the final layers of GPT, possibly caused by tied embedding and unembedding weights during training. This tying of weights may impact the model's behavior and could be a potential area for future exploration. Overall, the authors emphasize the importance of addressing the limitations of the study and delving deeper into understanding the intricacies of language models to advance the field further.